All right. So, where did we leave off? So we've been talking about implementation of our model, and we started by talking about nodes, right? Those are really the fundamental basis behind the overall model. They're establishing connected points between elements. Those elements may be the same element, they may be different elements, right? Beam to plate, to cable, or so on and so forth. But so nodes are important, and we've been going through this stuff pretty quickly. And I had a doctor's appointment yesterday, and I'll make an official announcement, but I'm not going to have class next week either. It is University Day on Friday, so we don't have class on Friday anyway. So we'll do a couple more recorded lectures. I am going to post the homework for this class. It won't be due until the Wednesday after next Wednesday, which is fine. Gives you guys plenty of time to work on it. It's not anything huge, but I really did want to spend at least that Monday, the week that it's due, kind of backtracking through some of this and talking about how this relates to VA and how you'd implement some of these, and kind of going through some of that. With respect to VA, I've mentioned it multiple times before. Start this. I've mentioned it multiple times before, but they have a huge archive of all of these educational videos. Granted, they're not all for visual analysis, and they're not going to all be applicable, right? Some of these are VA 17. Some of them are applicable between 17 and I think we're on 21 now. But they go through some very helpful tips and tricks and explanations of, what are member elements, and I was trying to find a good one here. Like reporting, that's going to be key as we continue to move on in class. You're going to, create this model. You're going to get results for this model, but filtering through all of the available information through VA can be kind of cumbersome. So it's nice to go out here and watch these videos. A lot of them are pretty short, right? Like 6 minutes, 3 minutes here and there. But they give you a lot of information and at least get you a step in the right direction to developing a good understanding of how to go through the mountains of information that comes out of our analysis. And so those are very helpful. There's some on areas and P delta analysis, but like area side results, those are going to be helpful later on as we get into more plate modeling. They talk about analysis errors and statics. Some of those troubleshooting and validation information. Plate results, right? That's a big one here on the left here. Plate results, because as we'll talk about here in a second, the local coordinates, global, and the results that come from those, it's a different coordinate system than we're used to relative to defining, especially our moments. And so that is definitely worth looking at. Auto meshed areas, there's another one there. So, there's 20, 30 minutes or more. I bet you could spend a few hours in here if you really wanted to, diving into kind of all of these little tips and tricks and introductions to a lot of the concepts of VA. And I'd also say for those of you that are working for a different firm or going to go out and work for a different firm, they're going to have a finite element analysis software tool, and they're all going to be fairly similar. So I don't think watching these videos is spinning your wheels or wasting any time. It's going to give you a little bit more of the background knowledge to kind of understand how this whole process works, implementing the FEA. So go out and check out some of those. I am going to end this class a little bit early. One, I'm going to try and get out another steel. Man, these drugs are really messing my head up. I'm going to try and get out another steel lecture today, as well as some homeworks through the weekend. So I'm going to let you guys out early. Also thought you would give you some time to maybe check out some of those videos and look at the homework and maybe piddle around with some of that a little bit more to kind of get yourselves a good understanding of VA. I know everyone's kind of at a different level. Some of you are probably Jedis at it, but others I definitely think are not, just relative to your experience. So, if you do have questions, as I've said before, work together, right? I don't want everyone to give me the same answer, especially on homeworks. But all of you have varying levels of understanding and experience with this program, so don't hesitate. And I think you all now have established relationships with each other well enough to be able to reach out to one another and get some help relative to homework or just general understanding of the software package. So don't feel bad about reaching out to others as well as reaching out to me too, right? So we talked about nodes, as I mentioned. That's really the critical one. There's a number of ways that you can define nodes in VA. And like I said, when I get back into class, I'll do a little bit of tutorial about that. Member elements, right? They're similar to nodes. They're an element, right? That's going to be defined by nodes at the ends. And we talked about earlier this week about the releases that you can impose upon those and how they're based on local coordinates. We also have to be aware of releases of our member and then overall global releases or supports, right? So we can over-release our model, which it leads to instabilities. Plates, right? So plates are similar to members. Okay. In that they're defined by our nodes, right? And that we can define releases. And we define releases based on degrees of freedom. So with our members, you can see at each node we have 6 degrees of freedom, right? Translation in 3 directions and rotation in 3 directions. Well, as we know from plates, we have a similar degree of freedom at each node, right? We have translation and rotation of each node. So each node has 6 degrees of freedom, right? And so we have the ability to disconnect or release the plate element to our nodes. And so the numbering of these nodes is not based on the node numbers. So if you go into VA and pull up in the model view, you draw in this, say, rectangular plate here. You click on the plate, and then on the left-hand side underneath the modify, it'll say releases, and then you'll get this drop down you see here. And so with these releases, the numbers 1, 2, 3, and 4 are just based on the numbering that was established based on drawing it. So if you started here and you drug your cursor around here, right, click on each one of those subsequent corners, we're gonna start by node 1, then go to node 2, node 3, and node 4, right? And so that's how the numbering is established. It's not going to change these numbers, right? This in the modify tab under releases, it's always going to be 1, 2, 3, or 4, or 1, 2, and 3 if you had a triangular plate element. And as we know already, VA is creating 4 triangles, right, within this in the background anyway. So all the time, VA is going to analyze this as a triangular almond triangle like we've talked about. But for us to impose releases, we're going to do so in such a way that we drew it. So this can be kind of tedious to see which nodes are which to release it. But the nodes, as I mentioned, are numbered at the local plate level and not the global node numbers, right? Every node that we develop in our model is going to increase, go up in numbers. We're going to start with node 1, 2, 3, 4, and keep on going. But we always are defining these node releases based on, 1, 2, and 3, or 1, 2, 3, 4, based on how we drew it, right? So not associated with node numbers, but to creation of the plate, okay? So we have 3 node versus 4 node plates. Our forces and moments are in the local direction. Right, up here with all those releases, they're all small values of X, Y, and Z, right? Lowercase x, y, and z. So we want to make sure that we look at the local coordinates, and that's what these are denoting here. So you'd go into your project manager, underneath your, I think it's filter tab. Under there, it'll say plates, and under plates, you can have it show local coordinates. And so that way you can see when they say MX, MY, and MZ, right, they're talking about the local coordinate directions. Another thing, and I've talked about this before, if we go out to the help file, and this is a piece of the help file that I actually printed off when I was working, and it was actually taped up in my office because I have the hardest time remembering the like how the sign convention works for plates. And so if we look at this plate element, okay, have our local coordinates of X, Y, and Z. The moment in the X direction isn't the moment around the X axis that we're used to. I think I've talked about this before, right? It's the moment on the X face, right? So this would be, these two here would be the X face of our plate, and that moment is applied on that plate to give stress in the X direction. Similarly, shear, right? So shear in the X, right, is going to be shear in the X face, right, in the X direction. It also gives a positive shear, so up on the left, or down on the left, up on the right. Is that right? Yeah. And so we also want to see, shear is acting at that coordinate face side, okay, not in the direction. And so you can see that's consistent with MY, MX. And this MXY, well, that's a shear in the X face in the Y direction, right? So it's on the X face, again, the blue shade here, but it's wrapping or creating stress in the Y direction. And so that's that MXY, and then there's MYX, right? So that'd be Y face, X direction. On top of all of this, there is a Z direction, and that is what they would call our drilling degree of freedom. And that's like if we took this whole plate and we tried to twist it about that Z-axis, right? So we're twisting about the Z-axis. And so that is the sign convention. You can see here they talk about positive moment produces tensile stresses on the positive local coordinate face of the element, right? So that's how they introduce sign convention. So when you look at your plate results, you'll know which direction the moment's acting based on this sign convention. You can also see the sign convention for tensile normal stresses, which are positive, right? Which is consistent with mechanics and how VA establishes it. Plate releases. Well, when we start modeling things, we're going to need to release some of our elements, right? So, I mean, there's thousands of different conditions, right, where we're using plates. Some of the big items that we use plates for in structural engineering relative to our main material types. For steel, it's usually, connecting plates, usually fairly large connecting plates. We also do in steel metal deck, like for a roof system. Usually you use like a corrugated metal deck. And you can, model it as a given thickness based on stiffness, and you can establish that stiffness based on engineering principles. We also use them for, as I mentioned, connection. So if we go to concrete, typically we use plates for wall elements or large footings, so mat slabs, slabs on grade, retaining walls, walls for like liquid retaining structures, water retaining structures. Those types of elements. And so those are big for concrete. If we look at concrete masonry units, CMU, it would be big retaining walls or shear walls for buildings. If we look at wood, big elements that we'd use in wood would be also shear walls, which we would then model a plate representing like the OSB or plywood sheathing on the outside of a building. That would typically be our shear wall material. And then you would have to, make sure you're modeling the stiffness appropriately to get the right results. So if we look at some of these, right, we use shear walls, common. As I mentioned, we use them in some plate connections. So if we had, those of you in, for everyone in steel, I guess except for Jocelyn, but even with steel 1, we talked about connections with, 2 plates with a fillet weld, right? This could be a shear tab attached to some column face or something like that, right? And we talked about the reasons for or wanting to weld on both sides. So typically we'd want to put a weld on both sides. But if we didn't put a weld on both sides, right, this plate, the strength of this plate, stiffness of this plate, in and out of the page is pretty significant, right? Inline shear along the length of this weld. But then if we start looking at, if we were to apply a force to the top of this plate, well, this thing's going to just kick out, right? It doesn't have a lot of flexural stiffness at that connection. So that might be a case where we would want to release some of the moments, right, along that edge of the plate. And so that might be a case where we'd want to take away that stiffness. If we didn't take away that stiffness, well, that would mean that if we provided any sort of loads, I'm trying to erase all this. If we provided loads to where we have demand at that location, right? So say we model it as if there's a fillet weld here. Well, now all of a sudden there's resistance to moment in this direction. Say we did have some loads maybe that were out of plane to this plate. Well, before, if this was pinned, they'd have to travel somewhere else throughout this connection, right? If we fix it, now all of a sudden we do have demands here. Well, if there are demands here and we try to design it with a fillet weld, and we go and we say, okay, we're going to design this fillet weld. What are my demands? I go to VA to pull out my demands. All of a sudden, I'm going to have an M, right? A moment in that direction that fillet weld needs to take. All of a sudden, shoot, I don't have the capacity because the fillet weld doesn't have any capacity for a moment like that by itself, single-sided. So then I go back and I say, well, all of a sudden now I need to put this fillet weld out, right? So it's kind of self-fulfilling, right? We could either assume that it's not there, make sure our releases are appropriate, make sure it acts as a pin in our model, and then we're going to, design that for those forces. Or if we, omit the release in the model, saying that it is fully restrained, right? There's no moment release. Well, all of a sudden now we're going to have demands. So when we go to design that fillet weld in the end, we're going to have moments on it, right? And so it's going to come up one way or the other. If we think about concrete, right? Some walls, so some wall intersections. Are going to need some thought relative to fixity, okay? So if we're looking at a retaining wall, so let's say that we're looking at this retaining wall right here, right? So the retaining wall right here, and that retaining wall, is based off of a footing, poured on the ground, and then this wall attached to that footing. Well, for some of you that have experience doing retaining walls, there's a couple different ways that we can model and design the wall itself. We can design the wall as if it acts as a true cantilever. So all of a sudden, we put a bunch of soil back here, right? And that soil is providing some amount of lateral earth pressure on this wall. And the wall behaves as a big cantilever. And if that's the case, this better be a fixed connection, right? We better be able to provide moment at that location. If it doesn't act as a cantilever, right? Well, some walls that retain soil are also restrained at the top. So, anybody who lives in a house in Bozeman that has a basement, right? It's going to have a concrete wall on it, around the perimeter. You're going to be hanging out in your basement here, right? And there's going to be a ceiling above you, right, that carries the first floor. That first floor could either be attached to the face or on top of the wall. It's not super important. But what it does do is it all of a sudden is now making this wall act as though there's a pin up here, right? And so you have the option as a designer sometimes, and it actually leads to usually a more economical shape or economical design, is that we pin the wall at the top, right? So now the wall cannot push over. So now it acts as you could have it as a fixed pin if you really wanted to, or a pin, right? I usually go with pin, and if that's the case, now all of a sudden your rebar obviously needs to stick to one side of our wall instead of originally being on the loaded face. Right? If this was a fixed wall, we'd want the reinforcement on the tension side of our wall, which would be on the loaded side. But now if it acts as a pinned or pin fixed, now all of a sudden we're really going to want our steel to be out here on the outside, or potentially if it's pin fixed, we might want it on the outside, out in the middle of the wall, and then at the base of the wall, maybe we want it closer to the inside, or sorry, the outside where the loading is. Get rid of some of this, a lot of extra stuff here. So again, all things that need to be decided as a designer. One other thing that sometimes comes into play is, you have a slab on grade usually in basements as well, right? And a slab on grade can sometimes, if you want to justify it, you can assume that slab on grade restrains the base of that wall from sliding. And maybe that acts as the restraint to help create that pin. Another thing to think about relative to walls and intersections. Okay, so in this case, we could, I guess, coming back to releases, in this case, we got to be aware of the behavior that we're going to design for, right? So relative to this wall, maybe it's pinned, maybe it's fixed, and maybe we want to release this, maybe we don't. If we do a box, say we're looking at a plan view of an elevator core or something like that, or a stairwell. So maybe we've got the landing, we've got stairs going down and then stairs going up on one side, right? So if, so we go up, around, right? So this is a stairwell and we have intersecting walls. I've talked about this briefly in class before, as I mentioned, about, continuity around corners. So if we have these 4 plates and we connect them at the corners and we push, this thing looks like a big stair tower, it's a big tube, and all of a sudden we put horizontal load on this tube, right? It's going to tell us, as we know, if there's continuity across this corner, that there's going to be, compressive stresses that exist around the corners. It's not just the flange that's going to carry that stress. It's going to wrap around the corners, right? And so as a designer, again, we have to decide, are we going to assume that there is continuity, right? With respect to translation and rotation between all of these plates, or maybe we want to release some of that. So there's the opportunity that maybe we release the vertical force between these two elements. So we could release one of these plates on one side. I've mentioned to you, sometimes what I've done is I've just doubled up nodes at these corners and actually just created independent plate walls that are extending up, but then are just gapped by a little bit. Again, there's a lot of different ways to do it, but these are some areas where you'd have to think about, well, how are the forces going to transfer? Or how do I want the forces to transfer across these intersections of elements? Let's see here. What else are we going to talk about? Membrane action. So we talked about this. The field house roof is a big membrane. So all we're doing is we're removing, so removal of degree of freedom in the out of plane direction. Okay. So we need to be careful about doing this, because even though maybe our behavior is predominantly in plane, like the roof on the field house is a good example. It acts predominantly as a membrane, but at the same time, we have all these loads that are on the roof of the field house, construction live loads. If they replace the roof, we have people standing on the roof. We have live loads, snow loads, dead loads from the insulation and membrane and all of the components maybe up on the roof, ventilation, ductwork and stuff like that. And so even though globally the behavior we're worried about is that this plate acts as a membrane, but at the same time, in order to get the loads distributed appropriately in our model, we need to distribute them to elements. That load is acting perpendicular to our plate element, If we create it as a membrane, but we load it in the perpendicular directions, we're gonna have problems, right? We're essentially loading an element that has no stiffness in that direction, and you'll have problems with your model. One of the beautiful parts about using areas is that you can still load an area, generate plates from an area, and then make those plates membrane only, and then still load the area perpendicular to the in plane direction of that area. And the area is going to distribute it based on supporting members. So it'll then distribute that load to all of our surrounding members, and it's going to skip the plate, even though because we have it as a membrane only behavior. So we just have to, or need to, be careful as out of plane stiffness will affect load path. Right. Again, like I mentioned, just with this fillet weld here, we kind of have self-fulfilling prophecies, I guess, if that's the right way to put it. But we're going to be designing this building, and we're making all these assumptions as to how this building behaves. And when we make these simplifications from the real world to our mathematical model to our finite element model, those assumptions we're making may or may not be super accurate, but the results that we get are based on those assumptions, and then the results are what we're actually designing the structure for in the end anyway. So we're going to provide it with a load path, and it's going to have adequate capacity, and so we might be all right anyway. And so we just have to be careful that if we use membrane-only behavior, that those out-of-plane forces need to be carried somewhere, and sometimes that can lead to total instability if there's no mechanism to distribute those forces, like I mentioned. If there's no area present or other members or things like that. Or it might just affect the way the plate behaves and how we might design the plates later on. Right, so membranes can't carry out of plane loads. Right? Essentially saying there's no bending. As I mentioned, this can lead to instability. Okay. All right, so with that, I think we're pretty close to 30 minutes. As I mentioned, give me a little extra time here to look at the homework, which I'll post here shortly. And then also take a look at some of those introductory videos to VA, a little self-study, if you will, on VA, because our first homework, this homework that I'm going to send out to you, is a VA exercise. And as I mentioned, I'll make an announcement as to how next week is going to be oriented, but it seems as though, based on doctors' comments, that it'd make sense to take one more week, which would be just 2 more lectures off, and I'd be back after Easter. So anyway, stay tuned for that as well, and I will